Hello, SGY2. This is going to be the worked answer to this old practice exam question. Parts A and B are very similar to what we did in the first lesson on rate laws, and parts C and D are something new to you, which are simply plug-and-chug questions where you use the rate law as an equation to find an unknown. So, let's start with A. Write the rate law and explain how you determine the orders. So I'm going to start with trials 1 and 2, because I can immediately see they held NO constant and they doubled BR2. When they did that, the rate also doubled. Great. So I can quickly compare these because it's 10 to the minus 3 and 10 to the minus 3. Those are the same and the number has doubled. Nice and easy. So that means BR2 is first order. Remember, when you do something to the concentration and the same thing happens to the rate, that's first order. For NO, we need to find trials where the BR2 is constant. And there's a couple options here, like I could do 1 and 4, but I want to keep my life easy, so I'm going to do 1 and 3. Because then, NO has doubled, BR2 is constant, and the rate has gone from 1.2 to 4.8. It has quadrupled, which means NO is second order. Second order means whatever you do to the concentration happens twice to the rate. So it's times 2 times 2. Okay, now for an exam question, that is not enough. Okay, we actually have to write out a justification. So let's practice doing that here at the bottom. So part A, the rate law, don't forget, don't be lazy, write the whole thing. Rate equals K. We said NO was second order and BR2 was first order. So I can just leave that off. To write your explanation, I would tell them which experiments you used, what was held constant, what changed, and what happened to the rate. So you're actually including the whole thought process in writing. So in experiments 1 and 2, NO was constant, BR2 doubled. You can write doubled, but I think this is just fine. A chemist will understand what you're writing, and on an AP exam when you're rushed, you want to save time. So BR2 times 2, rate also times 2. So BR2 is first order. Okay. That is a nice logical progression of thought that an examiner can follow. Do the exact same thing for NO. In experiments, what were they? 1 and 3 I think we used? Yep. In experiments 1 and 3, BR2 was constant. NO times 2, rate times 4. So NO is second order. Done. Part B. On the basis of the rate law, calculate the rate constant and specify its units. Okay, so this is where we plug in numbers and solve for K. It doesn't matter which trial we use. I'm going to use trial 1 simply because the concentrations are nice, easy numbers, 0.1. So the math will be simple. All right, so solve for K. K is rate divided by the concentration of NO squared times the concentration of BR2. And if I plug my numbers in, the rate was 1.20 times 10 to the minus 3. And both concentrations were 0.1. Okay, that's really nice. This is just 10 to the minus 3 down here. So that will cancel. And my K is just 1.20. Units. Use the same equation, but plug the units in. So rate is molar per second, molar squared, and another molar on the bottom. One of them will cancel, leaving you with molarity to the -2, seconds to the -1. I'll just put that up there. And I've got K. All right, C and D. Something a little new for you. Calculate the rate in trial 3 if the volume of the mixture is decreased to half. So they're just saying they want you to use this rate law with some new values. All right, we've got K. We need to know what are these two concentrations, NO and Br2. And if we look at trial 3, we have 0.2 and 0.1, but they're squishing the container by half. That means the concentrations are going to double. All right, so instead of 0.2 and 0.1, I'm going to plug in 0.4 and 0.2. There we go. Rate equals K, which we just calculated, 1.20. The concentration of NO, 0.2, but doubled because the container was halved. So 0.4 squared. And the Br2 doubled, 0.2. Put that in my calculator and I get 3.84 times 10 to the -2. It's a rate, so molar per second. Done. Let's look at D. Calculate the rate in trial 4 after NO has decreased to 0.15. Okay, this is a bit tricky. It's something that harked way back to Unit 1 last year when we did limiting reactants and we looked at how much of something has reacted. I'm going to show you a way to set this up that I think makes it really easy to visualize. So what's happening here? We're doing this reaction. We're starting with these amounts because we're in trial 4. And they're telling us the 0.3 has decreased 0.15, like the reaction's half over, basically. What's the rate when the reaction is half finished? To figure that out, you need to know what this one's going to be. And the temptation would be, oh, well, that one's half finished. It doesn't work that way. We need to use the balanced equation to figure out how much Br2 is left when half of that one has reacted. All right, here's a nice way to lay out that kind of working. Start with your balanced equation. 2NO plus Br2 goes to 2NOBr. And underneath of it, I use the acronym BCA. Before and after, and how much it must have changed by. So if I plug the numbers in, we said for trial 4, it starts as 0.3 and 0.1. And the problem tells us that there's only half of the NO left at this point. So how much has it changed by? Well, it's changed by half, and I'm actually going to put a negative in there because it's going down. What's great about this table is that this row, the change row, has to be according to the mole ratio. Because that's how they change. For every 2 molecules of NO, you react 1 molecule of Br2. For every mole of NO, for every 2 moles of NO, it's 1 mole of Br2. That's the ratio. So if 0.15 of NO reacted, half that amount of Br2 reacted, 0.075. I'm going to say that again. If 0.15 moles of NO reacts, half that number of moles Br2 has reacted. And the reason I know that is because this is 2 and this is 1. Has to be according to the mole ratio. Once I have that, I can subtract and see how much bromine is left. Okay. So these are the numbers that will be remaining in the vessel at the point they're talking about in question D. The hard part's finished. Now all we have to do is plug and chug. Rate equals, we know K is 1.2. We now know that NO is 0.15 and Br2 is 0.025. Make sure you use the squared from our rate law. And when I plug that in my calculator, I get 6.75 times 10 to the minus 4 molar per second. And that answer makes sense. It should be pretty slow. If the initial rate was 1.08 times 10 to the minus 2, as the reaction slows down, the rate decreases. All right, and there you have it.